For the last video, this will be a somewhat longer version of other videos. We will talk about heats of reactions. So first, let us talk about the energy diagrams. I will tackle this subject of focus because I will have some um, problems included in your quiz and term exam in terms of energy diagrams. So an energy diagram, by definition, is it just shows the relationship of the amount of heat in a chemical reaction with respect to time and the reaction progress. In general, it is any diagram with energy or heat. So as you can see, this is a sample of an energy diagram. So this is the amount of heat and the time or the reaction progress. So there are some parts that you need to know. And the common um, thing you will see is that first, it has a straight or a flat line, and then it will go up and then go down, and then it will have another flat line. So it can be this one is on a lower portion and this one is on a upper portion, and sometimes they are almost the same portion, and sometimes there is no significant um, ups and downs on the energy diagram. So the energy from this point minus this point is known to be as the activation energy, or AE, or A sub E. An activation energy is the amount of energy needed for the reaction to continue if it is an irreversible reaction, or not a non-spontaneous, rather non-spontaneous reaction. And the amount of energy from the first flat line to the second flat line, you will take the difference, and that is the standard enthalpy of the reaction if this is in standard, if this reaction is on standard molar scale. So as you can see, so the standard molar enthalpy, or the change in heat, it depends. If there are given, for example, this energy diagram is specifically for 50 grams of water only. But if there is no specific amount given, then it is the standard enthalpy. But if it has a specific amount given of the reactants, then it will have only the change in heat, or heat evolve. Now let's talk about Hess's law. So what is Hess's law? Hess's law is a the enthalpy of the reaction is the difference of the sum of the product of the enthalpy change of formation of the individual reactants and products and their respective coefficients. So sometimes the standard enthalpy or standard molar enthalpy of the reaction is not given, but we can find it by having the table of the standard enthalpy of formation of each product of or reactant. And in your quiz and term exam, I will give you a copy of that table so that you have um, a guide to solve or to find the actual standard enthalpy of reaction. Note that it also works with the change in entropy and gives free energy, but we will only solve for the enthalpy. So let's try this. Calculate the standard molar enthalpy of the reaction of 3 hydrogen gas plus ozone is yields 3 water. So first, let's just talk about that let's just take note that this is in equilibrium, or rather it is balance. So if the standard enthalpy of formation of each reactant and product is 0 kilojoules per mole of the hydrogen gas, 143 kilojoules per mole of the ozone, and negative 243 kilojoules per mole of the water. So that. Let's just use the given formula. So n and m are their respective coefficients. So it must be taken note of that we need to balance the equation first. So for example, water has a coefficient 3, so we will multiply this by its coefficient, 3 times negative 243. Then we need to subtract it from all of the reactants multiplied to its respective coefficients. For example, 3 and 0 for the hydrogen gas, and 0 and 1 for 1 and 1 for 3 rather in the ozone. So by putting it in your calculator, we will get 869 kilojoules per mole. I think I have a problem. It must be negative. Yeah, it must be in negative. I forgot to put that. So there's another way of solving the Hess's law, or the standard enthalpy of formation or reaction, without giving each of the standard enthalpy of the reaction of each um, reactant and product, and that is by the indirect method. The other one is the direct method, and this one is the indirect method. So in the indirect method, we will use other equations that include the necessary elements or compounds in our equation. And as you can see, we have carbon as graphite, just like what I've said earlier, that it can be anything, because there are times that carbon has very different properties as diamond compared to as charcoal and as graphite, added to half gas of oxygen and carbon monoxide. So what we will do here, so let's just take note of these two equations because these are the most important one. So as you can see, we will just need to add the equations in the way that we will obtain this equation. How? So let's first look at the graphite. This one, the first equation. Let's call it equation A. Equation A has graphite on the left hand side, oxygen gas on the left hand side, and carbon dioxide on the right hand side. So since both of the graphite and the oxygen gas are on the left hand side, then we will not reverse the equation. Next, the carbon monoxide is on the right hand side, oxygen gas is on the left hand side rather. Carbon monoxide is on the left hand side, oxygen gas is on the left hand side, and the carbon dioxide is on the right hand side. So we need to put carbon monoxide on the other side because it is shown in our necessary equation. So we need to reverse it. How? We just need to multiply it by negative 1. By multiplying by negative 1, this 2 will go on the right hand side and the carbon dioxide will go on the left hand side. Since we multiplied it by negative 1, this will be multiplied by negative 1 as well. So this will become positive. As you can see, next is we need to cancel out the necessary um, elements and compounds. So CO2 and CO2 have a coefficient of 1 and is on the other side of the equations, then we can cancel this out. O2 and half of the O2, meaning this will be canceled out, or if we put it on the other side, it will have minus 1/2 oxygen. So 1 minus 1/2 is just 1/2. And everything else will add. Next is we need to also add both of the heat of reaction. So minus, wait for a second. So again, let's just add both of the heat of reactions of both equation in the correct um, sign. So negative 393.5 plus 283, which yields that the heat of reaction of the equation is negative 110.5 kilojoules. Next is let's talk about the second to the last topic, which is the bond enthalpy. So when we are talking about enthalpies of gases, reactions of gases, we can use this one. It is the change in enthalpy when bonds of gaseous molecules are formed or broken. Note that it only works with gases. It is very difficult to work with solids and liquids. So let's take this for example. So this is C. There are three C's. There's one. So this is propionine. So this is propionine and chlorine gas, which yields one to one one to chloropropane propane 1,2-chloropropane. So these all of these are gases. And if you look at your lecture, you have there a table of the bond enthalpies, the respective bond enthalpies. But in this one, I will just provide you the bond enthalpies of each one. So how do we work with this? First is we need to know which um bonds are broken and which bonds are formed. So let's talk about this. So as you can see, Cl and CnCl, CnCl are formed. So we have two CnCl. Next is this one is broken down. So we have ClCl broken down. So we have CCl, two CCls, one Cl to Cl, and then another one is this two became one, or rather, the double bond became a single bond. So C double bond C is broken down, and then C single bond C is formed. As you can see, double bond of C double bond C is there's one C double bond C that is broken. There's one Cl to single bond Cl that is also broken, and the respective bond enthalpies are these, and we need to take the total of that. Next is the bonds form. So as I have said, C double bond C became C single bond C, and that is and then this is their bond enthalpy, and there are two C single bond Cl that has been formed, and this is the bond entropy. Since there are two, we need to multiply it by 2 and then take the total. And then by bond entropy, we just need to add both the bonds broken plus the bonds formed, and that is equal to 854 minus 1021. And overall, the heat of reaction, standard entropy of the reaction is negative 173 kilojoules per mole. Lastly is the spontaneity. The Gibbs free energy determines the favorability or feasibility of the reaction in terms of spontaneity. This is the Gibbs free energy, or the G, and it can be solved using the enthalpy and entropy of the reaction, as well as in terms of the temperature. So this is one example of um, a problem the in this subject of spontaneity. Carbon oxide, or rather calcium oxide, is produced from the decomposition of calcium carbonate. If the reaction is carried out at 25 degrees Celsius, is the reaction spontaneous? So I have already given you the um, enthalpy, standard enthalpy and the standard entropy of the reactions, and just since this the temperature is given, we need to convert in Celsius, we need to convert it in Kelvin. So 273 plus 25 is 298 Kelvin. And then by just substituting the necessary values, we will get 130 kilojoules per mole. Now, how do we know if it is spontaneous? If the Gibbs free energy is positive, then it is not spontaneous in that kind of reaction, but it is spontaneous in the reverse reaction. If the Gibbs free energy is negative, it is spontaneous on the forward reaction, but it is not spontaneous in the reverse reaction. If it is zero, then there's no reaction. So, how do we know which ones is forward and reverse reaction? This is the forward reaction, the decomposition. Now, if we reverse that, let's put the products to the reactants and the reactant to the products, then it is now in the reverse. So, since this is positive, meaning the decomposition of calcium carbonate is not spontaneous. It means it requires activation energy. If it if this happens, calcium oxide and carbon dioxide are together, then it is most possible that they do not need energy to form calcium carbonate, meaning they are spontaneous in the reverse reaction. Take note of that. Reverse only, not the forward reaction. So if you have more questions about our topic, please DM me in our consultation hours, and I hope that you learned something today. If you are having a lot of trouble in our topic, you can ask for help from us, or even to your advisors, and even we can have a consultation G meet as soon as possible. That, and I hope you're having a good day.